So I want to talk about global warming and update it to the present as best I can. And thinking about that, I grabbed some recent news headlines, including one that came out in the middle of the night. The melting of Antarctica was already bad. It just got worse. That was the Washington Post, came out about midnight last night. But a number of these things. 2014 broke the heat record. 2014 is officially on record as the warmest year we've had. We are beginning to understand better and better the relationship between energy and climate, something else I talk about and wrote a book about. John Kerry is telling us here that really is the solution to the problem. This last month was the first time CO2 levels surpassed 400 parts per million, basically steadily. They've been poking above it for about a year, but now they fully surpassed it. Sea level rise is a bigger problem than we thought. A map of what global warming is going to look like. The Arctic sea ice is getting thinner. You've heard all this. And I want to give you an update for 2015 with three really big questions. First of all, is the climate changing, and how do we know? What's the cause? Well, we're the cause by and large, not entirely, but mostly, and how do we know that? And then what of the future? And before I focus on the first question, I want to talk a little bit about what an update 2015 means. I am going to give you some really recent news about climate change, but mostly I'm going to be talking about the report of the Intergovernmental Panel on Climate Change. And you have probably heard about these reports. In fact, for the last couple years, you've probably heard people talk, oh, a new IPCC report, new horrors, new woes, new crisis. Well, some of that wasn't quite that new. The IPCC report is, in a sense, a single unified thing. It's been coming out gradually over the last couple of years. And I want to talk a little bit about that report, and I want to show you what it looks like. I don't usually like to travel with this, but here it is. This is the IPCC report. Actually, this is the report of Working Group 1 of the IPCC. These are the scientists. Working Group 2 is about impacts and adaptation and vulnerability, a lot of work by social scientists. And Working Group 3 is about mitigation of climate change. So this is the science one, and these are massive tomes, thousands of pages, 1,523 to be exact in this one. The second working group, the social science one, has 2 volumes about this thick, and the third one has another volume this thick. So it's a massive report. Not only that, in November you heard there was a new IPCC report. Well, it wasn't a new report, it was the synthesis report that puts all this together. So what's this IPCC? It gives out one of these reports about every 6 years. The latest one was released over the years 2013 to 14. This one says 2013 on it, but the later ones say 2014. It tries to describe the state of knowledge in the world on climate change as put together by the experts, and the IPCC report is good through about the year 2012. So we're already 3 years past this report in terms of our knowledge. There are 3 working groups, as I mentioned, 3 different volumes: physical science, impacts, adaptation, and vulnerability, and mitigation of climate change. So this is a big, massive report, and you've heard a lot about it. It is not, and then there's this synthesis report that I just mentioned, came out in November. This is not some left-wing crazy outfit that is trying to, foist climate change off on the world. This is an outfit which is producing these technical summaries and policymaker summaries for the policymakers of the world. They're approved by the 195 member countries. There are hundreds of authors from more than 70 countries. They're reviewed by experts from 84 countries, almost 2,000 of them. And all these documents, if you would like to go read them, you don't have to pay the $95 Cambridge University Press charges you for this. You can go out and read it free at www.ipcc.ch. They're all available free, everything, the graphics. And if you want hard copy, get it from Cambridge University Press. So I want to move on. How do we know climate is changing? What do we know about those changes? Here's a graph showing roughly what the temperature of the planet has looked like over roughly the last 1,000 years. And I'm going to show a lot of graphs. I apologize for that. That's probably not the language most of you speak in, but it is the language I speak in. A graph is worth 1,000 numbers. There's a lot of information in a graph. And my job when I show you a graph is to tell you what I'm graphing. If I don't tell you that, or somebody else talking throws a graph up and doesn't say anything about it, it doesn't tell you anything. So this is a graph that gives the year from the year 1000 to about the year 2000. This is the temperature deviation relative to some average, which doesn't matter in the least. It wouldn't affect the shape of that curve, so don't really worry about that, except that up is higher temperatures and down is lower temperatures. It turns out easier to measure and understand changes in temperature than actual values of temperature themselves. And you see the picture, and I ask my students when I show them this graph, if you had to describe this as a general trend, what would you say? If I said, just look at that and tell me what it says, sort of as a general trend, what do you see there? Really general. What happened for the first 900 years?
Nothing much.
Not much. And then what happened? It went way up. Now, does somebody want to be just slightly more subtle about what happened for the first 900 years?
Shut up.
Now, the first 900 years.
Average.
I mean, you said not much. Well, could you be just a little bit more specific? What did it do? Maybe it went down a little bit, and then, of course, it shot up. By the way, the wiggly part over here is actual data taken from thermometers, which we know quite accurately. The rest of this are reconstructions I'll talk about a little bit that are not actual temperature measurements, but pretty good proxies for them. Things like tree rings that tell us how trees have been growing, and so on. So is the temperature changing? Well, if you look at this, you see this kind of picture of gradual decline for 900 years, a very sharp uptick. This is called the hockey stick. Michael Mann, who first produced this graph when he was at the University of Massachusetts, Amherst, has had this name stick to him ever since. He came to Middlebury to speak, and I gave him a hockey stick signed by the national champion hockey team, and it hangs on his office to this day. That's the hockey stick graph. He got a lot of grief for this. The hockey stick graph figured in an earlier IPCC report, but then a whole bunch of other groups around the world tried to do the same work, and they all came up with pretty much the same thing for the last 1,000 years, and here we are at 1,000 on this graph. This one goes back 2,000 years. Gradual decline and this very sharp uptick. And the conclusion is something very unusual has happened in the last roughly 100 to 150 years. So let's take a closer look at that. So here are the temperatures during the Anthropocene. What is the Anthropocene? What does that mean? You may have heard of the Pleistocene or the Oocene or the Paleocene. What's the Anthropocene? It's the age of human, we're women too, so it's the age of human beings, the age in which we have come to dominate over nature. And this is actually, there's actually a big debate going on right now about adopting this term to describe the current epoch that we live in, the Anthropocene, the age in which humankind has dominated nature. And one of the issues is how do you define the start of that? A very recent suggestion for starting the Anthropocene was to when we started producing radioactive fallout, because that will be a marker in the rocks that will be forever available for people to see something happen. Or maybe when we produce plastics. Or I read another one just yesterday suggesting around 1600, human activity had gotten powerful enough to reverse a trend in declining carbon dioxide levels that would have continued into the next ice age, which is now not going to happen. So anyway, we're in the Anthropocene, and the Anthropocene temperatures during the time we've had actual measurements back to about 1850 look like this. Not much, as you said so carefully. Now, not much doesn't mean nothing. It means a lot of wiggling going on, but no general trend. And then some rises starting in the early 20th century, some little declines in the mid-20th century, probably caused by industrialization after World War II and coal burning. I'll have a little more to say about that. And then rapid rise in the late 20th century, followed by a kind of leveling, which I'll also say a little bit about. Now, if you take this same data, and you can go to this the website of the Climatic Research Unit of the University of East Anglia in England, which has the world's best climate records, many people think, and you can go and look at this data yourself and play with it and plot it, and that's what I have my students do the first day of class in my climate science class. But let's just take a look at, if you sort that data and look at what's the hottest years on record. So there are the top 10 of the hottest years on record. And something is pretty obvious. Which century are they in? With one exception, the 21st. And if we look at the next 10, there they are. The rest of them, all the years of the 21st century that we've had are in this realm, and the rest of them are all in the 1990s. You'll notice that 1992, 3, and 4 are missing. I'll tell you why that is a little bit later. There's a good reason for that. Each time I do this talk, I update this, and each time it gets more dramatic. The 80s dropped out a while ago. The 90s are on their way out. And I'm going to have to start distinguishing the 2010s from the 2000s. Of the 20 hottest years on record, they've all occurred in the last few decades, and most of them in the recent decade. So I had this playing when you came in, and I'm not going to spend a lot of time on it, but this is a reconstruction by NASA in which the yellow and red colors are higher temperatures, and you can see graphically that same data, how the temperature of the planet has been changing, and the more yellow and red there are, the hotter it is on average. And here we come up through the middle 20th century, and now toward the end of the 20th century, the 90s are coming on, and here we go, and redder and redder and redder. In 2013 we end. And so that is a graphical visualization of the climate change that has been happening based on those same temperature measurements. Now, I want to emphasize it isn't just temperature we're talking about. If it were just temperature, we wouldn't have much to go on, although the temperature has been increasing. Many other things are going on. For example, we've been setting record temperatures occasionally. In fact, this winter we've set some record lows. That's unusual. If you had a climate that wasn't changing, you would expect roughly equal numbers of record highs and record lows, because they're equally likely to get a little colder than usual, equally likely to get a little warmer than usual. So that's what it would look like if everything were normal. You'd have 50% record highs and 50% record lows. In the 1950s, you had a little bit more record highs, but not much. By 2012, when this data was put together, record highs accounted for about 90% of the records and record lows for only about 10%. Now that's a little bit year dependent, and maybe it's not the same in 2013 and 14, but you get the idea. The number of records being set, temperature records, most of them are now record high temperatures. That's another indication that the planet's warming, and it's not quite the same thing as saying the average temperature is going up. Sea level is rising. You've heard about sea level rise. You've heard all these horror stories about how Florida is going to disappear and so on. Well, it would take 3 meters, which we're not going to see in this century, to have Florida disappear. I just came back from a wonderful vacation on Sanibel Island, which is right about there, and it will not be there. Anything in red will not be there with 3 meters of sea level. But that's a few centuries out, but it's going to happen. So here's another one of these graphs. Year from 1880 to about 2010. In this case, these are 3 different data sets based on tide gauges, which are these instruments that sit in the ocean or looking down on the ocean with ultrasound and measure the height of the ocean. And it's not an easy thing to measure with waves and tides, but you can get an average value across the world, and that's been rising pretty steadily throughout the 20th century, basically. So sea level is rising. That's another indication that the climate is changing, and in particular that it's warming. Here's a more subtle one that people don't think about as much. You can ask yourself how much energy has been stored in the upper layers of the ocean as a result of the extra heat that's coming in. And the answer is quite a bit. Here's the ocean heat content, never mind the units, but it's going up this way. The heat content, here are 3 different averages of it. They're all basically saying the same thing, though. The ocean heat content from about 1950 to about 2014 has been increasing more or less steadily, a little bit slower in the last decade, a little bit faster before that, but basically it's increasing. More energy is being deposited in the Earth's system. Every year in September, usually, sometimes in August, but usually September, there comes a day after the Arctic summer is nearing its end when the maximum amount of melting has taken place and the ice pack in the Arctic Ocean has its minimum extent. And every year, the National Snow and Ice Data Center out in Colorado keeps track of when that day is, and they record the sea ice minimum at that time in square kilometers, in this case millions of square kilometers. And here's what it looked like in the late 20th century. Again, not much happening, maybe a slight downward trend, a lot of variation, but around 1990 or a little bit afterwards, we started this very steep decline. There was a really dramatic drop in 2007, and everybody said, well, that's a fluke, it's not going to be anywhere near that low again, but 2008 was almost as low. And then it came back up, but not way up, it came back up to following this very steep downward trend. 2012 was even lower, and then up here, we're back at 2013, I believe this is, and yeah, because we haven't had, maybe this is 2014, I'm going to think 7, 8, 9, 10, 11, 12, 13, came back up a bit, and I think we're roughly around here for 2014. But the main point is downward trend, and this gives rise to these iconic pictures like the poor polar bear sitting there on the chunk of ice. Here's a picture of that, composites made from satellite images of the Arctic. I don't have one for that for 2012 when it was really low, but 2007 was now the next lowest, and it looked something like that. The Arctic was largely open through here. You could get through the so famous Northwest Passage with a ship. There was no ice. Here's what it looked like in 1980. And this is still well into the modern era, and yet this change is quite dramatic. So the Arctic is shrinking. We have glaciers. Glaciers on land. Glaciers are ice masses on land, moving rivers of ice. Here are a number of glacier pairs. Here's in Glacier National Park, 1913, 2005, same glacier, same place. Glacier National Park is going to lose its name by about 2035. Glacier in Switzerland, 48, 2002, 2006, 1993 and 2000 on Mount Kilimanjaro. These are glaciers at about the equator, but high up. The Muir and Riggs glaciers in Alaska. There's the glacier way back there in 2004. There's a lake. There's what it looked like in 1941, and another pair in another glacier in Alaska, gone pretty much. So the glaciers are melting. The Antarctic ice sheets are collapsing. That piece of news I just picked up in the middle of the night was about the Antarctic ice sheet. It was about the East Antarctic ice sheet, the West Antarctic ice sheet we've known about for a while. And here's a famous collapse of a piece of ice that was larger than the state of Rhode Island in 2002. Now, it looks sort of like the ice sheet is actually growing, but it's not. This is open water. Here's the ice sheet, and the ice sheet is breaking off, and now this very thin layer of just temporary ice has filled that place, but the ice sheet itself is gone. It's broken up something the size of Rhode Island, and that particular event gave rise to models that suggest that we have now irreversibly started melting the West Antarctic ice sheet. So these glaciers, there's nothing we can do, at least on the time scale of a century or so, to halt this process now. It's just going to happen, and it's going to contribute to sea level rise. There are other indicators of how we know that the climate is changing. I mentioned ice and snow, but some other aspects of ice and snow. There's a decrease in recent decades in Arctic ice thickness. And this is something we couldn't have known until a decade or so ago when the Navy declassified the records of nuclear submarines that went under the Arctic ice pack in the 1950s during the Cold War. And they pinged their sonar up and they were able to measure the thickness of the ice sheet, but it was all classified. When that was released, we could put together records of the thickness of that ice pack, and we can see that that has been declining. We also look at things like the age of the ice, which is a more subtle thing, and more of the ice is newer, and less of the ice is surviving from one year to another. There's been a 40% decrease in the extent of Arctic ice. You saw that on those graphs of the declining Arctic ice. There's been a 10% decrease in global snow cover. You wouldn't know that in New England this year, but the northeastern United States is an anomaly right now in light of everything else that's happening in the world. It's an anomaly, by the way, that we understand, and it's occurring because of climate change. It's actually occurring most likely because of more open water in the Arctic, and that's what's causing us to have colder and snowier winters down here. There's a widespread retreat of glaciers that aren't the polar ice cap glaciers, but of these other glaciers I showed you. There are changes in weather patterns. The El Nino has been more frequent, it's been more persistent, and it's been more intense. There have been more intense precipitation events. When rain falls around the world, it falls in shorter but more intense bursts. Same for snow. Tropical storm intensity is increasing in some oceans, particularly the North Atlantic. Tropical storm intensity, but the frequency of tropical storms is not increasing. And I always tell my friends in climate change, particularly Bill McKibben, try not to make too much of bad weather. That's one of the things we have the least solid evidence for changes in. Some of it's there, some of it we can talk about. Certainly we can talk about intense precipitation, we can talk about some storms, and it gets great publicity, but that's one of the things we have the least solid grounding on. There are biological indicators. The growing season has been increasing at 1 to 4 days per decade. When I came to Middlebury College as a young twerp many years ago, I planted my tomatoes after graduation, and graduation at Middlebury is always on Memorial Day. I would go out and be pretty safe to plant my tomatoes then. I now plant them the first week in May, and I usually get away with it. I couldn't have done that when I first came to Middlebury College. Plant and animal ranges, they're shifting toward the poles at about 6 kilometers. That's about 4 miles every decade, every 10 years. And coral reefs around the world are bleaching. In fact, here's a funny word, phenology. What's phenology mean? It's not the thing where you look at your head and see what shape it is. What was that called? Phrenology. What's phenology? Anyone know what phenology is? So phenology is about sort of periodic life cycle events, things like when you build your nest, when you flower, when your buds burst and begin to make leaves and so on. So these periodic life cycle events in nature. And there was a meta-study done, a study of hundreds of studies of individual species. And here's what they concluded. Northern hemisphere species, as I said, are moving northward at about 6 kilometers every decade. Mountain species are moving upward about 6 meters in altitude, about 18 feet every decade. And that means a species out on Camel's Hump or Mount Abe or Mount Mansfield is heading toward the top, and if it gets too far up, there won't be any place for it to live anymore, and it will disappear, at least on that mountain. So mountain species are moving up, and spring events are typically occurring, typically earlier by about 2 to 3 days, 2.3 days per decade. And that includes nesting, breeding, bud burst, flowering, end of migration, all these things that are associated with the plants and animals returning in the spring. Okay, so how do we know all this? How do we take Earth's temperature? How do we do that? We can't just plug a big thermometer in. If we did, we get the temperature of the core, which is thousands of degrees. We don't want that. We want the surface temperature. Well, there are a whole bunch of data sets we have. We have, for example, sea surface temperatures, mostly taken by ships as they ply around the world. We have marine air temperatures, also taken by ships as they ply around the world, measuring the air temperature. We've got surface air temperatures taken by weather stations all around the world. You see weather stations here and there and everywhere. There's 1,200 of them in the United States that are monitored quite regularly. I think there's one of them in Manchester, but I'm not sure. And there are temperatures in the lower troposphere, the lower part of the atmosphere, that we get at in several ways, including weather balloons. And they all track in pretty much the same way. And since 1975, they've all been going up. We had a big year in 1998. We haven't got the new warmest year of 2014 on here yet. So they all agree is the point. We have to correct these data sets. I mean, how do you do this? You have thousands of measurements all around the globe. How do you combine them into one temperature for the planet? Well, as I said, that's hard to do. We can do it, but it's hard. It's easier to say, well, Manchester, Vermont went up 1 degree, and Sao Paulo, Brazil went up 1 degree. Now, we can't agree on what temperature it was, but we can agree on the changes, so it's easier to talk about the changes. So one thing we do is talk about changes. But we also have to make a number of corrections. For example, over the years, instruments have changed, and the people who do this work have to understand how the instruments were different. There was a time in the 1930s when thermometers in weather stations in the United States, ever seen a weather station? One of those little white boxes out there in somebody's backyard? And it's about yay high off the ground. It's about 1.5 meters off the ground, and that's the right height for it. It's got to be ventilated, and it's got to be sheltered from the sun so it doesn't get direct rays, and it's all these standards. Well, it turns out in the tropics they were lower. And that gives you a different temperature reading, and they have to correct for that. And we believe these data sets have been corrected. So another example, sea surface temperatures. Used to be they sampled the sea surface by plunging a bucket overboard, hauling the bucket up on the deck, measuring the temperature with a thermometer. Well, the ships got bigger, it took longer to haul the bucket up, the water cooled down or warmed up more, and the temperature changed. You had to count for that. Sometimes they used canvas buckets. And I remember when I was in the Boy Scouts, we had a great big canvas bag hung from a tree at summer camp to keep our water cool. Why did that work? Evaporation. The canvas leaked a little water out, evaporated, kept it cool. Well, same thing happened with those buckets. So when they changed from canvas buckets to wooden or metal buckets, they had to take that into account. And eventually they changed to looking at the water that was coming into the ship's engine intakes, and all that had to be accounted for. That's all been taken account of. One thing you'll hear a lot about, especially from climate skeptics, is, oh, there's this urban heat island. It's all due to the fact that we have urban heat island. What's the urban heat island? Well, there's what Boston looked like in the 1800s maybe, and if we put a thermometer in Boston, we would get a measure of the temperature. And then Boston grew. And cities are hot places. They're hot places because they got a lot of asphalt that absorbs sunlight and warms up. They are hot because they generate a lot of energy from fossil fuels mostly. And so they're hotter places than their surroundings. So if you have a weather station on the outskirts of a city, 100 years later, the city has grown, and now that area is urban, and it's going to read a higher temperature. And absent any other temperature trends in the world, the temperature would appear to go up based on these urban stations. Well, the point I want to make about that is we know what that effect is. One data set ignores it and says it's part of the error. It's about 0.05 of a degree, we think, is the error associated with that. Another data set takes it into account. You can throw out all the city weather stations to see exactly what effect it has. It's not a big effect. It's not the cause of the climate change or the temperature change we've observed over the last 100 years or so. This is a new one. I've never talked about this one before. I've sort of quietly ignored it as I've been talking about climate change in the last few years, but really I can't ignore it anymore. Here's a chunk of that graph of the Anthropocene temperatures based on some of those real temperature data sets. Here's 1998, which was very hot because of an El Nino, 2005, 2010, and the highest 2014. But it's pretty clear not much has happened in here, again, to use your phrase. Now, it's gone up and down, maybe a slight upward trend. But certainly in the late 20th century, we had a rapid warming, and now we have this so-called hiatus in which there's been little or no warming for the last 10 to 15 years. So what about that? Well, we think we know what caused it, or is causing it. There are some natural causes. It turns out there have been more small volcanic eruptions than we had thought. And volcanic eruptions put dust in the atmosphere that absorbs sunlight, and they put sulfate particles in the upper atmosphere that reflect sunlight and exert a cooling trend. And so there's been some cooling due to more volcanism than we thought. There's actually natural variability in the climate. The climate doesn't sit still absent human intervention. It varies naturally. And we don't understand all the mechanisms of that variation. And they're big enough still that they can, over short terms, mask the human effect, which is a gradual increase. So there's been some natural variability, and it's certainly been the case. So there's a graph of what a climate model predicts in the absence of human activities. It's a kind of natural variability that comes out of a climate model and probably out of the real climate also. And here's a graph of showing solar, the picture of the sun and ultraviolet light, but here is a graph showing the number of sunspots, and in the latest sunspot cycle, which was in the early 2000s, there's very little solar activity. The sun was actually putting out much less, not much less, but a little bit less energy than normally, and we think that contributed a little bit to the lack of warming over the last roughly 15 years. It's almost certainly going to turn around any day now. And the fact that 2014 was the warmest is maybe a hint of things to come. But there are plenty of other things that are not in hiatus. The ocean heat content, the amount of energy we're dumping into the ocean, the sea level, the ice melt, and most importantly, something I'm going to talk about next, the imbalance in the Earth's energy budget. And I want to move on to that. But the point I want to leave you with before I move on to sort of part two of my talk is we have a lot of evidence that the climate is changing, that the planet in particular is warming. I've even left out some I haven't even had time to talk about, but there's a lot of it, and it's not just about temperatures measured by thermometers going up. There's a lot of other things happening that are related to that, but aren't the same. So next, what's the cause and how do we know? So here's the big idea. The big idea is something I call energy balance. And here's how energy balance works. If you want to maintain a constant temperature, hey, it's a nice, comfortable 68 degrees Fahrenheit in this room. How on earth are we doing that? Because it's getting very cold. Mark Breen said this morning it's getting colder and colder and colder. Tonight it's going to be 10 out there. How come it's 68 in here? We're burning fossil fuels and heating the place. Okay? Now, why do we have to do that? Because if we turned off the fossil fuels, turned off the heat source, what would happen in this room? What would happen?
Colder.
It'd get colder. Why? What does it do? Where would the energy go? Out the windows, out the walls. Why do we have insulation in these walls? To slow that down. It still happens. So if this building were left alone, it would cool down. We have to supply heat to it at exactly the same rate it's going out through the walls. Now this is a nice new building. It's got lots of good insulation in it, so it doesn't go out at a very fast rate, so we don't need to burn that much fossil fuel to keep this, or maybe you run this on wood chips or something, or maybe you got a heat pump. What do you have here? What heats this building? Does anyone know? You Manchesterites should know that. Anyway, whatever's heating this building, you don't have to do as much of it because it's well insulated, but you have to do some. And tonight, because it's going to be very cold out, you're going to have to do more of it because the colder it is out, the bigger the temperature difference between inside and outside, the greater the rate at which heat is going to flow out. That's why you got to burn more fuel in the winter than in the fall or spring. Okay, it's that simple. So if the rate at which energy is coming into it, in this case from burning fossil fuels or the heat pump or whatever is making this place stay warm, is equal to the rate at which the energy is going out, then the temperature is going to stay the same. Now, in something like a building, we actively make that happen by controlling the heat source. But in a natural system like a planet, that happens also. And if you're out of balance, then the temperature either rises or falls, and it will naturally do that until a balance gets established. And that balance occurs for this reason, again, that the rate at which this building or whatever it is loses energy depends on the difference in the temperature between what's inside and what's outside. The bigger that difference, the more rapidly it loses energy. So if it gets really hot in here, it's going to lose energy really fast because it's going to make a bigger temperature difference. So even if we didn't have a thermostat, this room would eventually come into some kind of balance. And here's a very simple example I used to illustrate that. Here's a greenhouse. So this is a greenhouse, we want to grow plants in it or something, and outside it's cool, and inside we'd like it to be warm. And the energy is coming in from the sun because it's a greenhouse. But energy is also going out because it loses energy, like the walls of this room do, to the outside because it's warmer inside. And if it's in balance, those two arrows are just as big. There's as much energy coming in as going out. If it's really cool in the greenhouse, because it's cool, it's not much warmer than the outside, and so there won't be very much energy flowing out. If this building were at 15 degrees instead of 70 degrees, we wouldn't have much heat flow out to the 10-degree outside, because they'd be almost the same. So we don't have as much energy going up, but we still got this energy coming in, so more is coming in, so it's going to build up energy, and what's going to happen? What's going to happen if the energy comes in? More energy comes in than goes out. What happens if more money comes into your bank than goes out? You get more money, you get richer, it's going to get warmer. So the temperature is going to go up. On the other hand, if it's too hot in the greenhouse in some sense, then there will be a huge outflow of energy, more than is coming in, and it will naturally cool down. It will naturally seek a balance. And a planet does exactly the same thing, including planet Earth. So here's what the picture looks like for Earth. This is the same picture as the greenhouse, almost. Here comes the sunlight in. That's what delivers energy to Earth, and Earth heats up and it gives off energy. And it turns out the energy it gives off is in the form of infrared radiation, infrared light, invisible light that we can't see, that's redder than red, and that's what warm things give off. If you've ever seen anyone take a picture with an infrared camera, it's used for medical stuff sometimes. Take a picture of your face and you can see hot spots where there might be a tumor or a blocked blood vessel or something. That's the infrared light that you can't see. And the Earth had better be giving out exactly as much infrared light as is coming in from the sun, otherwise it's out of balance and it's going to either heat up or cool down. So if you do the math, and my students always do this the first week of class, you equate the amount of sunlight coming in, and I'm not going to do numbers here, to the infrared going out, and there's a formula for it that depends on temperature, because the higher the temperature, the more of this infrared is going to go out. You equate those, and you find that the temperature of the planet ought to be 255 kelvins, never mind what a Kelvin is, but that comes out about minus 18 degrees Celsius, or just about 0 degrees Fahrenheit, for the average temperature of the Earth. Now, does that sound right? If I said the average temperature of this planet is 0 degrees Fahrenheit, does that sound right? No. I mean, if I say the average temperature, in January of 2015 in Vermont, maybe that's about right. But that seems a little cool for the planet. On the other hand, it isn't really super cool. Because if it were super, if we come out really too cold, the whole planet would be frozen solid, as we believe, by the way, it once was briefly in something called snowball Earth. And also, it's not that hot. If it were really hot, the oceans would boil, as they did on Venus. So it's ballpark right, but it feels a little cold. Why is it cold? And it's cold because of the greenhouse effect that you've all heard about, which is what we worry about when we talk about global warming and climate change. Here's the greenhouse effect. The Earth has an atmosphere. So there's the atmosphere. And the atmosphere has, what's the atmosphere made of? Gases. What gases? Name me a dominant gas in the atmosphere. Oxygen, somebody say? What's even more dominant? Nitrogen. It's got 80% nitrogen, about 20% oxygen. The nitrogen was there naturally. The oxygen got put there by photosynthetic plants, whom we have to thank for that. But those gases are almost completely transparent to the sunlight coming in. That's why we can see the sun and the stars. And they're almost completely transparent to this infrared that's trying to get out. But there are some other gases that aren't. And you know which one is the biggest culprit there? Not CO2 first off the bat. It's actually another gas, even more common. Water vapor. Water vapor and CO2 are the predominant natural greenhouse gases. Water vapor and CO2. Methane is also one, but water vapor and CO2, mostly water vapor for this natural effect. And the result is these greenhouse gases get hot and they send some of the energy back to space and some of it down to Earth, and the Earth gets warmer. And it's warmer by about 60 degrees Fahrenheit than it would be otherwise. And the average temperature of the planet is, in fact, just about 59 or 60 degrees Fahrenheit. And we know all this. This is all physics. And by the way, we understand this process as it occurs on both Mars and Venus also, where both of them it occurs very differently on Earth because of their different atmospheres. So we understand this process. It's not some bizarre theory foisted on you by left-wing crazies. It's the physics of how these gases behave in the atmosphere. So the Earth is warmer than it would be, thank goodness, It would be habitable, but not very comfortable if the average temperature were 0. So we can thank the greenhouse effect for a nice habitable planet, warmer than it would be otherwise. The problem is we can enhance the greenhouse effect by adding more greenhouse gases to the atmosphere. So before I talk about that, I just want to give you 2 ways to understand the greenhouse effect. I think everybody in the world ought to know the term greenhouse effect and at least have some sense of what it means. And here's the easy way, and here's what your kids ought to understand, every kid in elementary school, and all of you ought to walk out of here, and you ought to know this. The greenhouse is sort of like an insulating blanket. I mean, you pull a blanket over yourself at night, and why are you warmer? Why does it feel warmer? What's the blanket do? It traps the heat that's trying to escape from your body. So your body doesn't have to work so hard to keep warm. You don't have to shiver and stuff. So that is a reasonable way of understanding the greenhouse effect. But a better way of understanding it is that the greenhouse gases actually absorb some of this outgoing infrared. They do block its escape to space, but they re-radiate some of it back to Earth. And that additional radiation warms the planet and makes it warmer than it would be otherwise. Here's the details. And my classes spend a couple weeks on this diagram. I'm going to spend a couple minutes. I don't care a whole lot about it, except to point out that what it shows is, on the left, this yellow stuff is sunlight coming in. Some of it's reflected by the atmosphere. Some of it's reflected by ice and deserts and stuff. And some of it gets absorbed by the surface, and some in the atmosphere. Here's the infrared going out. Some of it escapes right to space, not much. Most of it warms the atmosphere. Some of it goes off into space. Some of it comes back down, gets absorbed by the surface. There's a few other processes going on here. Very complicated. I don't care about that. What I want you to see, and this diagram, which first appeared about 4 years ago, is the first time we've had these numbers measured to this precision. Here's the actual total amount of incoming radiation. It's measured in watts on every square meter. You know what a watt is because you know what a 100-watt light bulb looks like. That's 100 watts. Well, this is watts. It's about 300-watt light bulbs equivalent shining down on each square meter of Earth's surface on average. But it's 341.3. And we know how much is going out. These are all being measured very accurately by satellites, and we know how much is reflected out. And so we can do a balance. And as recently as 10 or 15 years ago, we didn't have the numbers to do this balance, but now we can. So here's what's going out. 101.9 of them are getting reflected. 238.5 of them are going out as infrared, and that's 340.4 going out. But 341.3 of them are coming in. So if you do the math, there's an imbalance. And remember what happens if there's an imbalance. What happens to the temperature? It seeks a balance. It goes up or goes down trying to seek a balance. In this case, the imbalance is more energy coming in than going out. It's a positive 0.9 watts per square meter, and it means the Earth is absorbing energy at that rate. That is, to me, and to many climate scientists, probably the most fundamental indication that global warming is going on. It's not the one we know most accurately. We can't measure those numbers all that accurately, and some debate about whether that number is about 0.6 or 0.9, but it's a little less than 1 watt per square meter, and that's the imbalance. And that is most fundamentally what's warming the planet. It's the extra energy that's coming in over what's going out. And the reason we're out of balance is because of the greenhouse gases we've put in the atmosphere and several other effects that I'll mention briefly. So big, complicated picture, but the net bottom line from it is we are like that greenhouse when it's in a state of imbalance. We're losing less energy than we're gaining, and so the temperature must be going up. And if we didn't do anything else, we would come into balance at some new but slightly higher temperature. It's a few degrees higher. However, we are doing something else. We're continuing to pump greenhouse gases into the atmosphere, and so we aren't really approaching a balance because we're continuing to add to this effect. That number of 0.9 is going to continue to go up. Let's talk about some of the causes of this imbalance. Some of there are natural causes. The sun changes. It gets brighter and dimmer. Sends more energy to Earth or less. There's the solar cycle every 11 years. More sunspots, more solar activity, more energy coming from the sun. There are longer-term changes that we understand less well. There has been some long-term increase in the sun's output over the last couple hundred years. There is volcanism that puts dust and reflective particles in the atmosphere and cools the planet. And then there are anthropogenic effects, the most important of which are these so-called well-mixed greenhouse gases, like carbon dioxide and others, that live in the atmosphere long enough that they spread pretty much throughout the entire globe. Carbon dioxide, the most important. Methane, important. Those of us who are worried about gas pipelines in Vermont, methane is a strong greenhouse gas. If it leaks from those pipelines, it's 30 times worse than CO2 at absorbing this outgoing infrared. Nitrous oxide tends to come from agricultural processes. Another greenhouse gas. Ozone is a gas that gets produced from reactions of sunlight with car exhaust and things like that. There's the reflectivity of the planet. We go to the rainforest, we cut down the rainforest, and we grow crops to feed make McBurgers, to feed the cows that will make McBurgers. And the crops are lighter than the rainforest we cut down. They reflect more sunlight, they absorb less sunlight, and so that exerts a cooling effect. They send some sunlight back into space that would otherwise be absorbed, and we got to take that into account. In parts of the world, we are cutting down forests and leaving deserts. The deserts are more reflective, and so again, more sunlight goes back, and that's a cooling trend. There are aerosols, pollution, particles that we spew into the atmosphere. And most of them, not all, but most of them have the effect of reflecting more sunlight or keeping sunlight out of the system in some way. And so they exert a cooling trend. So a lot of the aerosols, that's why, remember I pointed out that the planet had cooled after World War II. That was largely the result probably of particles emitted into the atmosphere from the greatly increased coal burning with the increased industrial output. And the aerosols have two effects. One is direct. They reflect sunlight or do other things that affect the energy balance. The other thing they do is they affect the clouds. Because when you put particles in the atmosphere, there's a place for water to condense on, and that affects the nature of the clouds. It affects how much sunlight they reflect. I mean, you fly in an airplane above the clouds, they look bright, brilliant white. You look at them from below, they look dark. Well, exactly how they look depends a little bit on the size of the droplets, the height of the clouds. Clouds are one of the most complicated things in the climate system, and the thing we least understand, actually, and the thing that gives us the most uncertainty. But that's one way of talking about what clouds do. Both those effects of clouds, both those effects of particles, the direct effect of the particles themselves and their indirect effect on the clouds, probably result in a cooling. So, you may have heard the statement that, well, if we suddenly impose good pollution control on the whole planet, global warming would really take off. And it probably would, because we would put controls on the particulate matter emitted by coal-burning power plants, particularly, or by coming out the tailpipes of diesel trucks and things. And we would still be producing the greenhouse gas, carbon dioxide, but we wouldn't be producing these cooling effect particulates, and global warming would get worse. That's not an argument for pollution, but it is, in fact, something that's true. So to give you one more complicated graph that my students spend weeks on and then see on their final exam, but this is a simplified version of it, coming from the Summary for Policymakers in that Summary report that came out last November. This is a rough calculation of the different sources of climate change that are functioning today in the climate system, and roughly what their effects are in terms of temperature. So the observed warming since the start of the industrial era, about 1750, is somewhere on the order of 0.7 to 0.8 degrees Celsius between 1950, I'm sorry, not from 1750, this is only from 1950. From 1950 to 2010, we've warmed by about 0.7 of a degree Celsius. There was some warming before that, but the dominant warming has been since the mid-20th century. And so that's what that black bar means. To the right is warming. This is how much warming the greenhouse effect due to greenhouse gases would have produced, and we're uncertain by about that much, somewhere in that range for the observed warming. The other anthropogenic forcings is a word that means you're forcing the climate to change, you're forcing this imbalance, tend to be largely negative because they're associated with those aerosols. Great deal of uncertainty. We're pretty sure that's a negative effect, a cooling effect, but it could remotely by some chance be positive. You combine all those anthropogenic forcings, and they are just about producing a temperature change which is just about equal to what we observe. There are some natural forcings associated with volcanoes and the sun, and they're small. So when your climate skeptic uncle says, it's all caused by the sun, those effects are tiny compared to the effects of the anthropogenic substances that we're putting into the atmosphere. And there is natural internal variability also in the climate system, that again is hard to pin down, but it's small compared to the anthropogenic effects. So the takeaway message here is that the climate change we're seeing now is caused by anthropogenic effects and largely by greenhouse gases. And just to say a little bit more about greenhouse gases, here's where they're coming from, or here's what they are. Most of them are carbon dioxide from fossil fuels. Some of them are carbon dioxide from deforestation, from the decay of trees we cut down, and things like that. So put this one and this one together, and this one, which is carbon dioxide from making cement and a few other processes that produce carbon dioxide, and more than 3/4 of the fossil fuel of the greenhouse gases we're putting out are carbon dioxide. Next comes methane, natural gas from cows belching from their 4 stomachs. Termites, that's a natural source of methane. Leaks in natural gas pipelines, and so on. And nitrous oxide, largely from agriculture, and these are the fluorinated fluorocarbon gases, and they don't produce much, but they're there. So most of it is carbon dioxide. That's the take-home message. And where do they come from? Most of them from energy supply, the biggest single chunk, transportation, buildings, like the fossil fuels, if that's what we're doing to keep this building warm, industry, agriculture, forestry, and waste and wastewater. So these are the sources of the greenhouse gases by the sectors, by the things we human beings tend to do. Here's what CO2 has looked like in the historical record from about late 1800s on to the present, where we've just hit 400 parts per million, a little bit after 2000 on this scale. Those numbers we know very accurately. I send my students to study this all the time. In fact, one of the places where we measure this is on Mauna Loa in Hawaii, where there's a station that's been observing CO2 since the 1950s. And it's so sensitive, we see these wiggles. These wiggles are not noise. You know what those wiggles are caused by? They're caused by the seasons. Because when the plants come out, they put out leaves and they take what out of the atmosphere? CO2, and they make sugars with sunlight. And then when they shut down in the fall, they go out and say, wait a minute, we got a northern hemisphere and a southern hemisphere, but what's different about them? Which one's got more green plants? Think of a map of the world. Where's most of the land? North. And so it's a biased effect. I mean, Australia and South America and Africa don't make up for North America and Eurasia and so on. So we do see these fluctuations. And I always have my students plot 5 successive years from this data set. And they see that up and downness, and they can correlate it with the time of year very nicely. It starts going down in May or June, and it starts picking up again in the winter. And they plot 5 of them in a row, and they all lie in different places on the graph because the overall trend, of course, is upward. Look back 1,000 years. Remember that graph I showed you of temperatures over 1,000 years, the hockey stick, and you see it's been pretty steady at about 280 parts per million. That means take 1 million jugs of air, separate out the carbon dioxide, and early on in the pre-industrial era, there were about 280 of those jugs would have carbon dioxide, and today 400 of them would. And there's just some examples of some of the things we're doing that put out that carbon dioxide. Now, your uncle skeptic might say, well, how do you know this carbon dioxide came from people? We know that absolutely solidly. We know that because these fuels, the fossil fuels that are producing most of the carbon dioxide, are commercial. We get money for them. And so we keep track of them. We know how much is sold, we know how much is burned, and we track that consumption. That consumption is consistent with the increases in atmospheric carbon dioxide. More subtly, there's different isotopes, different kinds of carbon. One of them is radioactive. It's called carbon-14, and it's formed in the atmosphere. It's what archaeologists use to date things. And it goes away if you bury the carbon under the ground. And there isn't much carbon-14 in the new carbon going in the atmosphere, which suggests it's been hidden away from the atmosphere for a long time, i.e. buried. And there's another form called carbon-13 that is a little heavier than standard carbon-12, and plants don't like to do photosynthesis with it so much, so they don't take up as much of it. And there's less of that going in the atmosphere also, which suggests that the source of the carbon is plants. Plants that have been dead a long time and buried away from the atmosphere, and indeed that's what it is. And of course the fossil fuels have been buried for hundreds of millions of years, and they come from plants. And finally, the oxygen content of the atmosphere is measurably decreasing. Oh, can't breathe. Well, it's not that bad, but we can see the decrease in oxygen content, and it's consistent with the oxygen combining with carbon through fossil fuel combustion to make carbon dioxide. So we know that we have caused this trend, and carbon dioxide is going to be with us for a long, long time. And we know that the temperature of the planet and the carbon dioxide content of the atmosphere go hand in hand. Now, it isn't as simple as cause and effect. There's a lot of feedback mechanisms that make these things happen together. But this is a graph taking us back to 160,000 years before the present. Both these quantities, the temperature in the red curve and the carbon dioxide in the blue curve, were determined by measurements on ice cores drilled in Antarctica. That's where these numbers came from. but we think they're reflective of the entire planet. And you can see there was a warm spell about 120,000 years ago. And then there was a gradual cooling. What's that cool period called, that long cool period? You know, it's got a name. What's that called? What do you call those long cool periods the Earth goes through? Ice ages. Those are ice ages. And then we have these relatively short interglacial warm periods, of which we're in one now, and that's the one civilization evolved in. Now, this picture is up to about 2,000 years ago. Here's where we are today. We've taken carbon dioxide to levels the planet hasn't seen, according to this graph, for 160,000 years. This graph goes back 1 million years now, and it never gets much above here. And so we're at levels the planet hasn't seen for 1 million years, certainly, and probably for at least 20 million years. Now, it was higher in the age of the dinosaurs. But in the terms of the recent history, millions of years recent history, we've done something remarkable, and we've done it in such a short time. That really is a good graph. It's just the industrial era is so short on this time scale that it looks like a spike up. And if you saw Al Gore's movie, he looked at what this did, and he rode a big lift truck or something up and pointed to where it would be in the middle of the 21st century, but it's already impressively at 400 parts per million. My good friend Bill McKibben, I was at an event with him last night in Middlebury. So you recognize Bill McKibben. Who's this? It's a friend of Bill McKibben's. You know who that is? That's Jim Hansen, the climatologist, outspoken climatologist who first testified before Congress in the 1980s about climate change. And Bill McKibben, and they're good friends, and Bill asked Jim, what should be the safe level of carbon dioxide in the atmosphere? And Jim said, I'll have to figure that out, because he's a scientist. So he and a bunch of his colleagues, about 14 of them, wrote this paper, Target Atmospheric CO2, Where Should Humanity Aim? And they published it in 2008. And this one I try to tell all my students who are running around waving the 350 banner, most of whom have no idea what this is about. And you really ought to know where it comes from. And I try to have them read this paper. And this is a graph from that paper, and it shows the time, millions of years, that's what that stands for, before the present. So here's the present, and we're going back to about 60 million years ago. And the important point of this graph is there came a time before about 35 million years ago when the planet was ice-free. There was no ice. At least there were no big ice sheets or glaciers, things like that. No ice. And before that time, the CO2 was above 450 parts per million. And then at about 35 million years ago, it dropped below 450, and the Antarctic ice sheet began to form. The dark blue is when it was more intense. The light blue is when there was less. And quite a while later, only about 10 million years ago, the northern hemisphere ice sheets began to form. So the takeaway message from this graph is, if you get above 450 parts per million and you stay there for a long time, no ice. And there's about 200 feet worth of sea level rise locked up in the ice on the planet. It's mostly in Antarctica and Greenland. If that ice melts, sea level will rise by about 200 feet. And you can imagine what that will do to the planet. I showed you Florida at 6 feet. No, 9 feet, 3 meters, 200 feet. Much of humanity lives within 200 feet of sea level. I don't know where Manchester is. Middlebury's 350 feet, so we'd be okay. But a lot of places wouldn't be. So this is a problem, 450. Now, it's not going to happen immediately. It's going to take thousands of years, but it's a problem. And that is part of what led Jim to say to Bill, 350. And so the 350 movement got born. And there's other arguments for it, but that's one thing that argues for 350. So let me end with the last of my big questions. What is the future? What are our projections for climate change? Now, these get complicated looking. They come from computer models. How do you know that we can believe these computer models? Remember I showed you the 20 warmest years on record, and I said some were missing. Remember which were missing? 92, 93, 94. That's because Mount Pinatubo erupted in the Philippines in 1991, and global temperatures dropped by about half a degree quite quickly because of the dust put out by that prodigious volcanic eruption, and then they recovered over the next few years. And the red graph here are the actual observed temperatures, and the dotted lines are two different models that Jim Hansen and his colleagues at the Goddard Institute for Space Studies ran to predict what the planet's going to do. That is an experiment that nature gave us that showed that our climate models were right. Here are experiments run with climate models. The blue curve are models run that have volcanoes and solar changes that we know about in them, but they don't have any human activity, no greenhouse gases. And the pink are the ones with the greenhouse gases, and the black is the observations, and you tell me which one fits the observations, the black. The climate models seem to work, and they are also telling us they need the greenhouse gases that we know we've emitted in order to accurately tell us what the climate has been. We can do more subtle things. We can ask about patterns of precipitation. The observed pattern has this thing that looks like a goose with a lot of precipitation at the equator and these wings heading upward here in the Pacific Ocean. And here's the projected climate run from a climate model that was started back in the 1800s and run forward in time to the present and said, what does the precipitation look like? And it's pretty similar. That's pretty impressive. So we believe these models. What of our future? What can we expect? And what will be the impacts on us? And what can we do to mitigate it? Well, the answers to those questions are not obvious because they depend on what we do. This is no longer just a science question. It's a question about how humanity is going to react. And something that's new in the IPCC's fifth assessment report, this massive tome, is a new way of looking at these future scenarios. And the new way is these things called RCPs. And if you get into the IPCC report, you'll hear about those. And they're listed by number, and they give the approximate anthropogenic forcing, the imbalance in watts per square meter that we will have imposed on the climate system. RCP 8.5, that's a big watts per square meter imbalance. We've already imposed about 2.3, although some of them have been taken away by the rising temperatures. Business as usual, big. And 2.6 probably requires us to actually remove carbon from the atmosphere. And it's the only one with a chance of limiting the temperature in the industrial era to a rise of no more than 2 degrees. And you remember the meeting at Copenhagen a few years ago when the nations of the world couldn't agree on much, but they did agree we don't want the world's temperature rise by more than 2 degrees due to human activities. Well, there's only one scenario, and it's an almost impossible one. It not only requires us to stop putting greenhouse gases in the atmosphere, but actually to remove them. And here is what these radiative forcings look like under these models, these imbalances. Here is what the CO2 concentrations look like under 8.5. We get up to about 1,200 parts per million. That's what it was like during the age of the dinosaurs, yeah.
In this model right here, what is the assumption on population growth?
That's a good question. In the previous IPCC report, there were specific assumptions about that. Some of the models had it peaking in the mid-century and going down. Others had it continuing to grow. These models don't make that assumption. They simply say there will be pathways by which we emit this much carbon dioxide. They don't talk about the question of population. So they're different that way. They are based on scenarios of how much imbalance we're going to impose on the climate system. No, just this is what humanity is going to do. They don't talk about population at all. But it's a very good question, and the previous models, population played a big role. Good question. So, but my point is, here is pre-industrial carbon dioxide at about 280 parts per million. Here is twice that at about 560. 3 of these scenarios get above that. Remember what it took to melt all the ice? 450. So doubling is way more than melting all the ice. But again, it's going to take thousands of years to do that. And only this 2.6 one keeps us below doubling of pre-industrial carbon dioxide. What do the temperature increases look like? Well, here they are for these different scenarios. Here's sort of a range of them, but they range from anywhere from, and these are global surface temperature changes from about the year 2000. So before 2000, it's less than 0. It means it was cooler than that. And then it begins to go up. And the maximum is about a 6-degree increase here. The most extreme, probably more likely about 3 or 4 degree increase. And only one of these scenarios actually results in the temperature beginning to decline toward the end of the century. Here are maps of what the distribution of temperature looks like. If you're under this scenario where we actually remove greenhouse gases, it's still warmer in the Arctic. Everything is still warmed. And you'll notice that the land masses warm more than the oceans. And you can see the same thing here under this business as usual scenario, but now the temperature rises are very extreme, especially in the Arctic. Why do a few degrees matter? They matter because this is a global average. If I say the temperature is going to go up 2 degrees, a lot of places are going to warm up more. In particular, all the land areas are going to warm up more. The Arctic is going to warm up more, and that has a big influence on the rest of the planet. A few degrees is significant. The last ice age was about, on average, 6 degrees cooler than it is now. And what was it like here in Vermont under those conditions? 2 miles of ice on top of us. That's the difference 6 degrees makes. Now we're talking about changes in the coming century, probably less than 6 degrees, but at the outset it could be as high as that, but in the other direction. So that's climatologically very significant. And the other important thing is, if the mean goes up a little bit. Here's sort of a distribution of temperatures. You know, most of the time it's around 15 or 16 degrees here. If the mean goes up a little bit, the average day seems pretty much the same. But if you look at the extremes out here, you find that the curve is much higher on the extremes. And so you get much greater extremes, even with a small shift in temperature. So a small rise in the mean temperature greatly increases the probability of these extremes. Let me wrap up with just a couple of other things that are happening. Sea level is going to rise, it's rising and it's going to rise, and here are the rises in sea level projected over the coming century in these different scenarios. Here's the business as usual scenario, and the most extreme, probably not going to happen, is about 1 meter. That much. Adding on all the storm surges and all the tides and everything else. That's big. More likely about 0.5 meter, somewhere in the middle here. Could be as low as 20 centimeters, but very unlikely. That's what sea level rise is projected to be by the end of the century. And ironically, sea level rise is not the same everywhere. You think the sea is flat, but it isn't. So it varies in different places. It's actually quite high off the coast of New England, for example. Ice and snow are going to decline under these different scenarios. The business as usual scenario gives us an ice-free Arctic by the end of the century. Snow cover on the planet is declining, different amounts under different scenarios, but it's declining. And one thing I haven't mentioned, the carbon dioxide we're putting in the atmosphere, some of it gets absorbed in the ocean where it makes an acid, and it makes it hard for shell-bearing creatures to form, and it affects the ecology of the oceans quite dramatically. And that's independent of the warming. This is a chemical effect due to the carbon dioxide. So if we put lots of junk in the atmosphere to try to reflect sunlight to cool things down again, which I think is a very bad idea, it won't affect ocean acidification. Here's the ocean getting more acid under these scenarios. So let me wrap up. Best guesses for what's going to happen in this century. We're going to see a temperature increase of something like 3 degrees Celsius or about 5 degrees Fahrenheit. We're going to see a roughly 0.5 meter of sea level rise, about 18 inches, but it could be more, it could be less. We're going to see ice and snow coming down by about 20%, and we're going to see the ocean becoming more acid, dropping by about 0.3 in pH, which actually doubles the acidity. Okay, let me end with one last slide, which looks in the longer view, out 1,000 years. It doesn't stop at the year 2100. Almost all the scenarios you hear for climate change are what's going to happen at the end of this century, by the end of this century. But even if we peak our CO2 emissions somewhere in the next century, and they start to decline, and they've declined significantly by 100 years from now, it's going to be a long time before the temperature stabilizes, a few centuries. It's going to be a long time before the level of CO2 in the atmosphere stabilizes. We can decrease our emissions, but that won't take CO2 out of the atmosphere at any time soon. Sea level is going to continue to rise because the oceans are warming, and it's only the top layers that have warmed so far. And as that warming penetrates down, the whole ocean acts like a big thermometer and expands. And that's what causes half of sea level rise. The rest is caused by melting ice. That's going to take centuries to stabilize. And finally, the melting of large ice sheets, which will happen if we go over 450 parts per million, all of them, that's going to take thousands of years. So we're worried about the next century, but somebody ought to be looking ahead and worrying about that also. There's a good side to this, which is we've stopped the next ice age from happening, which would not have been a very good thing, but we got other problems coming. So I'll stop there. I hope you've got an update on global warming in this year, 2015. Thanks. And I'm happy to take lots of questions.
Any good news? I mean,
Okay. No, there actually, you know, actually, I didn't emphasize it, but in my news that I showed you in the third slide, there was one ray of hope. And there it is. In 2014, for the first time, which we can keep track of this data, the emissions of greenhouse gases by energy producers, that is, by electric power plants burning coal primarily, leveled off. It was the first year we didn't see an increase in those emissions. That's a very good sign. And John Kerry, if you read what he's talking about, he points out a lot of good things that happen. There are wonderful things happening. I mean, how many solar farms did I pass driving down here from Middlebury? I mean, I must have passed 10 of them. You know, and I've always been advocating photovoltaic energy as one of our solutions. I never dreamed that it would come so fast. That's got a long ways to go still. We got to put 5 of those farms in every town in Vermont. Now, up in Addison County, we have more than 5 in every town, but if we put 5 in every one of the 251 towns in Vermont, we would replace the electricity we were buying from Vermont Yankee before we had a squabble with them about it and started buying it from other nuclear plants in other places. You know, we need to do a lot more, but good things are happening. The question is, can we turn this thing around fast enough? And can we do it in the face of industrialization in other parts of the world that have every right to industrialize as we did? You know, I'm talking about China, of course. China's building coal-burning power plants very rapidly, but they're also the world leader in renewable energy. So I think there are signs of hope. I think we can do things. And, you know, despite the 350 people running around saying global crisis, it's not clear to me that this is the same kind of crisis as getting hit by a big asteroid or having a nuclear war would be. I mean, I think there are worse things that could happen to humanity. Not that I advocate for global warming, but I think we can muddle our way through this. We can mitigate it. We can turn it around. We have to do it. There's some sign that we're doing that faster than we would have expected that we were doing it, but we have a long way to go to get to those scenarios that bring us actually down. Very good question. Yeah.
I don't understand how these models can not talk about population.
Well, so that's a good question. The models that were used in the IPCC 4, which were there was something called the Special Report on Emission Scenarios, they included estimates of, you know, what would be the per capita carbon dioxide emission and things like that. And they necessarily took population into account. These new models simply say, what happens if, by the year 2100, we have upset the balance of the climate by this much? And they don't say how it happens. They don't say it happens because China and India all reach the United States standard of living, or because the United States gets even worse than we are, leaving them. They don't talk about why. Surely population is a huge driver of climate change, no question. But yeah, as is consumption. But my point is, the current models the IPCC is using don't make assumptions about that. They make assumptions about, you know, how much we're going to upset the balance, and surely that is going to be worse if there's more. So I'm not saying population doesn't affect it. It's implied, but it's not built in. It was built into the earlier IPCC report.
Thank you.
Yep.
What caused the dramatic drop in CO2 from prehistoric times? About 10 slides.
Yeah, good question. So, yeah, this is over a much longer time scale. This is 10 million years. And these are natural variations. This peak up here in temperature is interesting. It's called the Paleo-Eocene thermal maximum, and it is believed to have been caused by eruptions of methane frozen on the seabed into the atmosphere, giving rise to a very rapid temperature change. What causes the long-term variations here are subtle things like variations in the shape of the Earth's orbit, variations in volcanism, because volcanoes, which put CO2 in the atmosphere, are sort of the ultimate regulator of the Earth's temperature over hundreds of millions of year timescales. So there's a lot of geology and geophysics and probably some biology going on in here too. But that is not a steep drop. That's occurring over 20 million years.
You just mentioned the release of methane. To what degree do we get a multiplier effect by warming of the northern tundras?
That's a good question. So the northern tundras, of course, have permafrost, frozen ground, and that frozen ground traps a lot of methane. And one of the big worries is, as it warms, that methane comes out. Strong greenhouse gas causes more warming. My colleague, Andy Lloyd, who's our Dean of Faculty at Middlebury, she's an ecologist, and she spends her summers in Alaska studying exactly these kinds of questions. How are those feedback effects occurring that tend to exacerbate Arctic warming? And we don't have a good answer to that, but it's a very worrisome. Is that sort of your question?
I mean, as you say, the methane dissolved in the ocean.
The methane, there isn't much methane dissolved in the ocean, but there's methane frozen in these things at the bottom, and energy companies are actually looking, maybe they can harvest these things. But there's a worry about, you know, if these things require high pressure and low temperatures, and if those change subtly, we could get a bad feedback effect of methane bursting forth from the ocean.
I have a question about the scientific community.
Okay.
I'm not a scientist. I'm an advertising marketing background where I used to work. struggling to understand, and I'll paraphrase the numbers because, we marketing can't do numbers, that 97% of the scientists believe this. And I see numbers that like 30% of Americans think that global warming is it's just a total hoax. I struggle, other than some of the political issues, because it's related to political affiliation, understanding why the scientific community has not gotten this strong and powerful word out as much.
That's a very good question, and there have been some, by the way, recent polls. I think your 35% is about right, but it used to be more like 50% just a few years ago. It's gotten better. The American public is catching on. Part of it is, as we're always told, here I am, I'm a teacher at a liberal arts college. I dabble in climate change as a researcher. I know how to teach, but most of my colleagues, they're much better at doing climate science than I am, but they aren't necessarily very good at communicating it. Jim Hansen is a great guy. He gives the worst talk I've ever heard. But he gives big talks, draws big audiences in scientific meetings. But, we have learned that as scientists, the scientific community, that telling you the facts isn't enough. It doesn't really help. And, you're sort of an educated audience interested in this stuff, and I give you a sort of scientific perspective on it. But if there's a climate skeptic sitting in the room, they're unlikely to have their mind change. Now, I did teach a course a number of years ago in the Middlebury's Alumni College with my colleague John Isham, who's an economist, a little closer to your environmental economist, and we had a wealthy investment banker who was a real climate skeptic. And he took this course for a week, came out of it convinced, and he gave all the money for Middlebury's new environmental center. And that was a success. But we're usually that successful. But it's partly the fault of us scientists. It's also partly the fault of the public. I just went to a talk. We had a symposium Friday on science and religion. And there was a talk by a guy from Emory University on why it's easier to believe in God than to believe in evolution or something. That was the title of his book. And, I don't know that I agreed with him, but he gave some arguments about why it's hard to convince people of scientific facts. Good question. Yeah.
Now, I have another sort of take on this. Everybody's probably feeling very down. These are very depressing. Yeah. And it almost seems so removed from our life. I'm on the Dorset Energy Committee. So I can't help but say we can each do things that make a difference.
Yep.
Weatherize our houses, use a clothesline, walk, bike.
Yep.
So I think we ought to bring it down a little bit to that so that people feel responsible.
I agree completely.
And in the process of doing those things, you get to lead a simpler life and maybe affect the legislators more. In Vermont, we're very, very lucky.
We could also, we don't want to do this though, we could move to more energy efficient places like Manhattan. We were just having a debate last night. There's a new book by my colleagues Chris Kleiza and Steve Tromulak called The Story of Vermont, actually second edition. We had a panel discussion on it last night with Bill McKibben. And the question was, does Burlington need to grow to be a much bigger urban center in order that rural Vermont can survive? Because rural Vermont is not an energy efficient way to live, unfortunately. But there aren't very many of us. It's a good point. No, I'm not as depressed by this. I'm not horribly depressed by climate change. It's not, these pictures of the world melting and everybody going up in flames, it's not going to be that. Some of my bigger concerns are, it's going to affect the rich-poor gap in, what's this island nation, begins with V, I can't even pronounce it, just had the typhoon. Well, they got a lot worse hit by it because sea level is higher than it used to be. We got to, when the Bangladeshi farmers are up to their waists in water, Bill McKibben is fond of pointing out, well, they're up to here because of us in the United States. So we have to, there's some things we got to do, but I'm not quite as depressed by it. It's a challenge. Okay, well, thank you for having me.